Hello everyone, today we're going to solve a Diophantine equation, which in this case is just one equation. So basically what a Diophantine equation is, most of the time, just one equation with at least two or more variables. Now if these variables could be any complex number, it could be anything, then the equation would have an infinite number of solutions. However, a Diophantine equation is different in the fact that the variables are usually restricted to being only integers. In this case, the two variables m and n can only be positive integers. So that means instead of having an infinite number of solutions, there are only a certain number of solutions, which is what we have to find. So this is the 2012 AIME 2, number 1, and we just have to find the number of ordered pairs of positive integers solution m and n to the equation 20m plus 12n equals 2012. So let's just get into it. Now, the first thing that I notice is that obviously all of these terms are divisible by 2. Heck, they're divisible by 4. So let's just get that out of the way. Let's divide all of these by 4. So we get 5m plus 3n equals 503. Okay, we got the easy part out of the way. Now what? Well, we could solve for one of these variables, and let's see where we can go from there. So let's just solve the equation for m, because why not? So if we subtract 3 on both sides and then divide by 5, we get m equals 503 minus 3n divided by 5. Okay, so now what? So this is usually a part of the Diophantine equation where you usually have to get a little clever. There's almost always more than one way to solve this right here, but the easiest way that I can see in which to solve it is to use modular arithmetic. Now this is what I mean by that. We want this right here to be an integer. If this is an integer, then we find a pair of positive integer solutions. So we want this expression, 503 minus 3n, to be divisible by 5. So what we have to find is when 503 minus 3n is divisible by 5. Well, we know one thing. 503 is equal to 3 mod 5. Now what I mean by that is when you divide 5 by 503, you have 3 remaining. And this is pretty obvious, right? 5 divides 500 really easily, so 503 would have a remainder of 3. So if 503 is 3 mod 5, then what would 3n over here have to be in order for it to be divisible by 5? Well, 3n has to be equal to 3 mod 5. Now why is that? Well, when you subtract these from each other, 503 minus 3n, you're going to be subtracting these two. So when you subtract 503 minus 3n, you're going to get 0 mod 5. So it's a bit weird modular arithmetic, but it's basically the same idea. It's basically saying that if you turn 503 into 3 and 3n into 3, and you subtract them from one another, you're going to get 0 in the modular world. So what we need is for 3n to be equal to 3 mod 5. Now, working with 3n can be a little tricky, so let's just turn it into n. Divide by 3 on both sides, you have n equals 1 mod 5. So this is kind of a weird thing you can do with modular arithmetic. You can actually perform normal division and multiplication and addition and subtraction. There are a couple rules, but we won't get into that now. But just know that you can divide by constants in the modular world. So this means n is equal to 1 mod 5. And just like that, we've set our boundaries for what n can be. What I mean by that is that now we have to find all n's which go all the way up to a value in which it doesn't make this negative. Because keep in mind, if the numerator is negative, then that means this whole term is negative. Then that means m is negative. But we want all positive integer solutions. So we have to find, so the smallest n value is obviously 1, right? So if we have 503 minus 3 times 1, we'll have 500 divided by 5, and that's an integer, and that's a solution pair. Now, so that's the smallest number. What's the biggest value of n we can have? Well, what we have to do there is just just guess and check some values for n in which this numerator value doesn't go less than 0. So let's see. You can check 160, you can check 150, but I'm just going to say right now that 166 would work. Because if you put 166 here, I'll just do this. 166 times 3, you got 18, 19, 498. So if we subtract 498 from 503, we get 5. 5 divided by 5 is 1, m equals 1. That's a solution pair. If we go even more, then that would not work. Anything more would make this negative. Well, I mean, if we add another 3, we just don't get an integer over here. But if we add, say, 2 3s, so if we add 6, then we'll get 503 minus 504, and that will just make the numerator negative, so that's automatically not going to work. So we know that all n values have to go from 1 to 166. However, it isn't that simple. It's not like n is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No. It actually is 1 to 166 with a jump of 6. Now with a jump of 5. Now why is that? Well, remember, n is equal to 1 mod 5. So 166 is 1 mod 5. 1 is 1 mod 5. Now what do we do after 1? Well, we can't have 2. 2 is not 1 mod 5. 2 is just 2 mod 5, right? We can't have 3. Can't have 4 for the same reasons. We can't have 5. 5 is just 0 mod 5. But we can have 6. 6 equals 1 mod 5 because 6 divided by 5 has a remainder of 1. So, in actuality, this pattern is going 1 to 6 to 11, on and on and on to 166. Like this. So it's going to go like this. So we have to count all of these terms somehow. And this, in my opinion, is the usually the most tricky part, is counting the actual number of solutions in a Diophantine equation. But this is how I'm going to do it. There are a lot of ways to do it, but this is what I like to do. We can set up a arithmetic sequence. Sorry, series, not sequence, series. So we got one. It isn't a series, it's a sequence. A sequence is just a list of numbers, a series is a sum of numbers. Okay, so we got 1 plus 5. Man, why do I make that mistake all the time? 5n equals 166. So, what does that mean? So, what we're trying to find is this n. Actually, no, let me put a different value, just so I don't confuse. So we have this x value. So 1 plus 5x equals 166. If we find this x value, which, if you just do the math, is 33, that means that there are 33 solution sets from 1 to 166 minus 1. Now, why is that? This 33 is not correct. Not yet. This 33 accounts for all the numbers 6, 11, 16, 21, all the way to 166. It does not count this 1. So, if you were to put 33, you would get it wrong. And I'm pretty sure that's what a lot of people actually did put, because they forgot that this 1 right here is also a solution. This equation doesn't account for this 1 right here. So, instead of 33, we have to add another set, so we get 34 n values, so 34 n values equals 34 m values, which equals 34 positive integer solutions for that equation. And we are done. So this is a really basic Diophantine equation. It can get a lot more trickier the more difficult you go. In many cases, you actually have to factor the Diophantine equations in ways that makes it easier to group into solutions. But for now, this is a really good basic question to get your feet in the water and to just test it out. So yeah, if you have any questions, please let me know and make it a good day.